Hello there. In this video we're going to discuss a common operation that is used throughout advanced mathematics, and that is the factorial operator, which, for example, 5 factorial is written 5 with an exclamation mark that follows it. So in this video we're going to be describing exactly what this means and also talking about a few important properties associated with this particular operator. Alright, so the first thing that we need to do is actually define what a factorial actually is. We're not going to be talking about the applications of factorials here, just how to calculate them and some properties for them. So, definition. So we're going to let n be a natural number. So numbers such as 1, 2, 3, 4, and so on. Then n factorial is the product of it with its preceding natural numbers. So in particular, n factorial is going to be m multiplied by the natural number next to it, less than it, m minus 1, times m minus 2, times all the way down to the last natural number, which is 1. So since multiplication is commutative, we can actually rearrange this product in another way. For example, we can rewrite this as n factorial is equal to 1 times 2 times 3 times all the way up to m minus 1 times n. So we already know how to write this in pi notation, so therefore we can take n factorial and write it as the product from k is equal to 1 to n of k. So this is the more compact definition of the factorial operator or function. In particular, n here is a natural number. So let's just do a couple examples in case you are not familiar with this thing. So if I ask you what is 3 factorial equal to, so this is going to be 3 times 2 times 1, which is of course going to be 6. And if somebody asks you, well, what is the value of 5 factorial? So that's going to be 5 times 4 times 3 times 2 times 1. So we already know what 3 times 2 times 1 is, so this is equal to 6. So we can rewrite this as 5 times 4 times 6, since that's 3 factorial. So we have 20 times 6, which we know is 120. So there is an extension that is often done, and that is to give meaning to 0 factorial. So of course 0 factorial does not really fit in the definition for which we started. So what would make sense? So let's look at n factorial. So we know that this is equal to n times m minus 1 times m minus 2 all the way down to 1. So one thing we can write is that we can rewrite this in terms of factorials itself. So therefore n factorial is the same as n times m minus 1 factorial. So this is a special property, right? So what we can do is we can let n be equal to 1, right? So when we let n be equal to 1, we get 1 factorial on the left is equal to 1 times 1 minus 1 factorial on the right hand side. So we have 1, so 1 factorial we know is equal to 1 is going to be equal to 1 minus 1, which is 0 factorial. So we know that this expression is undefined by the definition, right, that we take. So what we can do is we can define 0 factorial to be equal to 1 by definition. So therefore, our definition is for factorial formally. So definition. So n factorial is equal to the product from k is equal to 1 to m of k for n in the natural numbers, and 0 factorial equals 1. So this is our, I guess, piecewise definition of the factorial function. Keep in mind, this argument here is not a proof. This is not an algebraic proof because this expression is not defined based on our definition. This just gives us an idea of one possible value that the factorial could be equal to, right? All right, great. So let's work out a couple more examples on factorial expressions and how to sort of simplify them. So first example, suppose we have 7 factorial over 6 factorial, 3 factorial. So we know 7 factorial is the same as 7 times 6 factorial all over 6 factorial times 3 factorial. So 6 factorial can cancel here. So we're just going to be left with 7 divided by 3 factorial, and we know 3 factorial is 3 times 2, so this is the same as 7 sixths. Another example. So suppose we have 12 factorial over 7 factorial times 5 factorial on bottom. So we're going to do the same. So this is going to be 12 times 11 times 10 times 9 times 8 times 7 all the way down times 7, and then we have 5, 4, 3, 2, and 1. So 7 factorials can cancel, and you can pretty much see why I expanded 12 factorial down to 7, because I knew that was going to cancel with something on the bottom. Right? So what else can sort of cancel here? So we have 4 times 3 is going to cancel with 12, and also 5 times 2 can cancel with 10. Right? So this is going to be equal to 11 times 9 times 8. So that's going to be 99 times 8. So that's going to be 792. All right, so let's do another fun example. Let's assume we want to find the sum from k is equal to 0 to 5 of negative 1 to the power of k divided by k factorial. All right, so what's this going to be equal to? So remember, this summation notation means sum over the values of k from 0 to 5. So this is going to be negative 1 to the 0, 0 factorial, plus negative 1 to the first, 1 factorial, negative 1 to the second, 2 factorial, negative 1 to the third, 3 factorial, negative 1 to the fourth, 4 factorial, and then negative 1 to the 5 over 5 factorial. Right? So these negative 1 to the powers are going to alternate between plus and minus 1. So we can rewrite this as positive 1 over 0 factorial, which is 1. And then we have minus 1 over 1 plus 1 over 2 minus 1 over 6 plus 1 over 24 minus 1 over 120. So we know 1 minus 1 is 0, and then we have 1 half minus 1 6 plus 1/24 minus 120. And then you can use a common denominator strategy to sort of get what that would be equal to. So what is this? So this is going to be 1 over 2 minus 1 over 6 plus 1 over 24 minus 1 over 20, right? Let's see here. So one thing I can do, actually, I'm just going to leave the details for you in case you're interested. So once you work out all those details, you should get this as equal to 11 over 30 once you simplify. All right. Let's assume we want to find the sum from k is equal to 3 of 3 factorial over k factorial times 3 minus k factorial. So remember, 3 minus k factorial is not going to make sense if k is greater than 3. So that's why I pretty much stopped my sum at that stage. Right? So notice 3 factorial doesn't depend on k, so I can sort of factor that out of the sum. So it's going to be equal to 3 factorial multiplied by the sum across all k. So we have 1 over 0 factorial, 3 minus 0, plus 1 over 1 factorial, 3 minus 1, plus 1 over 2 factorial, 3 minus 2, and then plus 1 over 3 factorial times 3 minus 3. Right? So we have 3 factorial there. So we have 1 divided by, so we have 0 factorial, which is 1, 3 minus 0 is 3, and then we have 3 factorial there, plus 1 divided by, so that's 1, that's 2 factorial. And then this is going to be, so that's 1 here, that's 2, so it's 2 factorial. And then we have 3 factorial on the bottom of that. So then I can distribute my 3 factorial backwards. And that's going to cancel with that, just leaving with 1 and 1. So this is going to be equal to 1 plus 1 half plus 1 half plus 1. What? No, just kidding, just kidding. So we have what? 3 factorial over 3 factorial. So we have 3 left because the 2 factorials cancel out of that. Then we have 3 as well. So we have 3 plus 3 is 6 plus 1 plus 1 is going to be 8. Right? So this is going to be equal to the same as 2 cubed. I'm going to rewrite this temporarily because this is going to lead into a property that we're going to prove at a later time. So let us assume we want to find the sum from k is equal to 6 of 6 factorial over k factorial times 6 minus k factorial. When combined, using the same exact procedure, this is going to be equal to 2 to the power of 6, or 64. Right? So again, you can generalize this property, which we'll prove later once we have or discuss our methods of proofs. The sum from k is equal to 0 to m of n factorial over k factorial times n minus k factorial. This is going to be equal to 2 to the power of n. And this is going to come in handy later on. So this is just a brief introduction to factorials and how to calculate them, and also a couple properties and shortcuts on how to simplify particular expressions. Hope you enjoyed.